This is section 8.1, part C, constructing a confidence interval. Why settle for a 95% confidence interval estimating an unknown parameter? The price we pay for greater confidence is a wider interval. If we are satisfied with 80% confidence, then our interval of plausible values for the parameter will be much narrower than if we insist on a 90 or 95 or even a 99% confidence. But we will also be much less confident in our estimate. Taking this to an extreme, what if we want an estimate with 100% confidence of the proportion of P of all U.S. adults who use Twitter? That's easy. We are 100% confident that the interval from 0 to 1 captures the true proportion of the population. Let's look a bit more closely at the method we used earlier to calculate an approximate 95% confidence interval for Mr. Schill's mystery mean. We started with our estimate plus or minus some margin of error. Our point estimate comes from the sample statistic X bar, which was 240.79. What about the margin of error? Since the sample distribution of X bar is normal, about 95% of the values of X bar will lie within 2 standard deviations of the mystery mean. So we can look at the following picture below. So the values of X bar could be anywhere in this normal distribution. We're going to look at the one right in the middle, and we're going to say it's within so many standard deviations of the sample. Now remember, a sample standard deviation is the standard deviation for the entire population divided by the square root of the sample size. Now, our standard deviation was 20 for this, and we did a sample size of 16. So that's 20 divided by 4, which is what's giving us that 5 for our standard deviation of the sample. We can rewrite our interval as 240.79 plus or minus 2 times 5, where remember 5 is the standard deviation of the sample. And we know we're talking about the standard deviation of the sample when it says sigma sub X bar. It's not just sigma, which is the standard deviation for the population. This is the standard deviation of our sampling distribution. This leads to a more general formula for a confidence interval. You're going to take your statistic plus or minus the critical value times the standard deviation of the statistic. Now, the critical value is going to depend on the confidence level C of the sampling distribution of our statistic. The only reason we were using 2 is because we were looking at a 95% confidence interval. And we know 95% of all data points fall within 2 standard deviations of the mean on a normal curve. But if we change it to a different confidence level, then that's going to change what that critical value is. So the confidence interval for estimating a population parameter has that form when the statistic we use is the point estimator for the parameter. The confidence interval for the mystery mean mu of Mr. Schill's population illustrates several important properties that are shared by all confidence intervals in common use. The user chooses the confidence level, and the margin of error follows from that choice. We would like high confidence and also a small margin of error. High confidence says that our method almost always gives correct answers. A small margin of error says that we have pinned down the parameters quite precisely. Our general formula for a confidence interval is our statistic plus or minus the margin of error, where your margin of error is your critical value times the standard deviation of the statistic. We can see that the margin of error depends on both that critical value and the standard deviation of the statistic. The critical value is tied directly to your confidence level, so greater confidence requires a larger critical value. The standard deviation of the statistic depends on the sample size n. Larger samples give more precise estimates, which means less variability in our statistic. So the margin of error gets smaller when the confidence level decreases. There is a trade-off between the confidence level and the margin of error. To obtain a smaller margin of error from a sample data, you must be willing to accept lower confidence. Earlier, we found that 95% of Mr. Schill's mystery mean would be between 230.79 and 250.79. If we want to narrow that confidence interval, we would have to have a smaller confidence level. So if we change it to an 80% confidence interval, then it's from 234.39 to 279.19. So as we can see, that interval gets smaller, but so does our confidence level. The other thing we can do if we want to have a margin of error that is smaller is to increase your sample size. So increasing the sample size reduces the margin of error by making the standard deviation for the sample smaller. So you do have two options. To reduce the margin of error, you can either lower your confidence level or increase your sample size. Before calculating a confidence interval for mu or for p, there are three important conditions that you should check. First, you need to check that it's random. The data should come from a well-designed random sample or randomized experiment. Otherwise, there is no scope for inference to a population or inference about cause and effect. If we cannot draw conclusions beyond the data at hand, then there is not much point in constructing a confidence interval. Another important reason for random selection or random assignment is to introduce chance into the data production process. We can model chance behavior with a probability distribution, like we did in Chapter 7. Next, you need to check to make sure that it's normal. The methods we use to construct confidence intervals for mu or p depend on the fact that the sampling distribution is approximately normal. So if we're looking at means, or X bars, the sample distribution is exactly normal if the population distribution is normal. But when our population distribution is not normal, or we don't know if it's normal or not, the central limit theorem tells us that as long as our sample size is at least 30, we can assume the sampling distribution will be normal. When we're dealing with proportions to check for normal or normal approximation, remember you're going to do n times p has to be greater than or equal to 10, or your sample size times the probability of success has to be greater than or equal to 10, and your sample size times the probability of failure must be greater than or equal to 10. We also need to make sure that they're independent. So before you can actually find the standard deviation of your sample, you need to check for independence. To do this, it needs to have with replacement, or if you don't know if it's with replacement or you know it's not with replacement, you need to check that 10% condition. So you need to make sure that your population is large enough that your sample is not more than 10%. To do that, if you know your sample size, you can multiply it by 10, and as long as your population is guaranteed to be larger than that number, then that 10% condition is met, and you can find the standard deviation of your sample. So again, the conditions that you need to be able to construct a confidence interval: you need to make sure your data is random, you need to make sure the sampling distribution is approximately normal, and you need to make sure it's independent, so they sample with replacement, or if it's without replacement, that the 10% condition is met. Here are two other important reminders for constructing and interpreting confidence intervals. Our method of calculation assumes that the data come from a simple random sample of size n from a population of interest. Other types of random samples, such as stratified or cluster, might be preferred to a simple random sample in a given setting, but they require more complex calculations than the ones we're going to be using. The margin of error in a confidence interval covers only chance variation due to random sampling or random assignment. The margin of error is obtained from a sampling distribution or randomized distribution in an experiment.